Assalamualaikum and good morning to the examiners. My name is Mazura binti Ramli, student ID 2020605174, and my supervisor is Dr. Wan Muhammad Ashraf bin Wan Mahmud. In this video, I will present my final project titled Optical and Spectroscopic Method for Detection and Analyzing Forgery Activities coupled with Chemometric Analysis. What is forensic document examination? Forensic document examination is a scientific discipline that examines question document and include ink analysis, which in the study, the analysis was performed using video spectral comparator, FTIR coupled with chemometry. This examination purposely first to determine whether there is any alteration on documents, second to differentiate the inks, and lastly to identify the original of the ink on the documents. What is the forensic ink analysis? It is the study of the inks, pigments, dye and other material used on forged document. The Star reported Azam and J used a forged bank account statement to apply a tender worth more than 2 million ringgit Malaysia. However, the problem of ink analysis arises when the alteration of documents made with different pen is occasionally invisible to human eye. In the previous study, chromatographic techniques were preferred among the analysts. However, the methods were disruptive. In ink analysis, the discrimination of inks also sometimes become challenging, as the inks from different brands can have slightly similar formulations. This study significantly gives future references to the Document Examination Division at the Malaysia Department of Chemistry in detecting the forgery of question document. The objective of this study are first to determine the feasibility of VSC in detecting the fraudulent document, second, to profile chemical component in inks using FTIR, and lastly, to discriminate the ink via statistical analysis of PCA and LDA. First, we look at the VSC for the literature review. This device allows us to analyze ink and visualize hidden security features, thus revealing an alteration on the question documents. This technique is a non-disruptive and it is a digital imaging system where light sources can be changed from the visible to near IR spectrum. This device features allows ink to be observed to luminance, be transparent or appear unchanged depending on its chemical composition. In a previous study of Giri in 2022, the number 4 was observed to be no changes under visible light, while the number 4 glow under IR radiation with wave number 645 nanometer. Next, FTIR was used to examine the chemical properties of the ink from the question document. This technique is non-disruptive as there is no prior sample preparation and it gives information about the presence of all organic groups in the examined sample. This table shows the common absorption pattern among all ink samples to their peak. This analysis is difficult to distinguish ink sample from similar ink formulation as it can result in similar spectra. Chemometric techniques that will be used in this study are principal component analysis and linear discriminant analysis. Both techniques will improve the discriminant power to provide detailed information regarding the discrimination of the inks. These statistical techniques are significant analytical tools, especially when working with complex multi-component datasets, as they can maximize the information extracted from large datasets. Both pictures on this slide show successful ink discrimination in previous study using PCA and LDA. The next part is methodology. This slide shows the sample that I used in this study. The method started when the check was visualized using VSC under different lights. Then the checks were examined to determine the functional groups of the ink using FTIR. Lastly, the spectral data from FTIR were computed for PCA and LDA analysis. For the result, the checks will successfully visualize the addition of TY and 0 on the check using VSC under fluorescent light with a 668 long pass filter. For the check A, the luminescent behavior of the altered ink was more clearly visible and shiny than the origin. However, for the check B, the luminescent behavior of the origin ink was more apparent and shining than the altered ink. Next, for the check C, the luminescent behavior of the origin ink was darker than the altered ink. For the check D, the luminescent behavior of the altered ink displayed a more pronounced than the origin ink. This variation observation under VSC is due to the ink formulation where the chemical composition reacts differently with the light used. The check 1 shows negative results, since the original and altered ink exhibit no changes in luminescent behavior. This negative result can be presumed that the origin and altered ink have comparable chemical composition. FTIR was performed to profile the chemical composition of the ink. The analysis was performed on the 5 sample objects in suspected forged region. As can be seen from the spectra, all the origin and altered ink exhibited similar peak profiles and position with slight difference in peak width and intensity. The spectra also majority display a broad peak at 3000 to 3700 per centimeter, which characterize NH2 group absorption, or occasionally overlap due to intermolecular hydrogen bonding from the OH hydroxyl functional group. The NH2 group is absorbed by the ink, whereas the OH group might be absorbed by the moisture. Black inks are commonly made up from the carbon-based compound. For analyzing ballpoint pen ink, the most significant region is from 650 to 1800 per centimeter. The table on the slide displays the simplified functional group present for each origin and altered ink used in the sample type A, B, C, D, and E. For the first wave number range in the table, the stretching bond vibration of CH3 and CH2 were found. For the second wave number, the peak region reveals benzene alcohol, whereas the peak in third wave number range, it may reveal the aromatic ether vibration. Next, the band absorption around the 1026 per centimeter indicates the primary alcohol bond. Furthermore, the mono-substituted arene group peaks occurred at 5th wave number range, suggesting to phenoxyethanol was used as a solvent in the inks, whereas for the last wave number range, the mono-substituted aromatic bending vibration was found in that range. Some of the chemicals found in ink and paper contain oxygen functional group, which could explain the presence of a peak at around 870 per centimeter. As a result of their shared similarities in composition across functional groups, it was unable to assign a unique classification to each black ballpoint pen ink. These chemometric techniques focus on the prominent peak wave number within 3000 until 1000 per centimeter. For the first result of PCA is the result of origin ink on the region 1 edition of TY. From the scatter plot, only 4 well-resolved clusters were observed, which accounted for 82.4% of the total variance in the dataset. However, only 3 clusters show good discrimination of the origin ink. The other clusters may comprise ink from the black ballpoint pen with a similar formulation. For the LDA, the cross-validation percentage was reported as 96.25% correct classification of pen sample, which can be observed on the scatter plot. Only 4 clusters successfully discriminated 3 ink pen samples. The study was further tested by testing the PCA and LDA on the altered ink. Results show a total variance of 72.8% in the dataset. Hence, only 2 clusters can be seen on the graph, where only 1 ink can be discriminated, while the other cluster was not well discriminated. It may be due to the similar formulation in inks. LDA was then performed for better classification of the given variance. The cross-validation percentage recorded 98.17% of correct ink classification, with 3 main clusters of different pen brand were successfully distinguished. The testing model of PCA and LDA then analyzed to characterize all the origin and altered ink. This figure demonstrated only 3 well-resolved clusters, accounting for 69.8% of the total variance. On the contrary, most of the ink did not exhibit clear clustering. At this particular point, PCA may not be sufficient. Then LDA was carried out to resolve the issue. There were 6 clusters in this figure, with a cross-validation of 94.81%. One of the clusters might comprise the ink with the same formulation or from the same ink. For region 2 edition of 0, the PCA scatter plot for the origin ink recorded a total variance of 96.3%. However, all the origin inks were not discriminated against one another. For the LDA, the graph demonstrated only 4 clusters with a correct classification of 96.46%, and 3 ink samples were well discriminated. For the altered ink on region 2, the PCA model scatter plot 2 clusters, accounting for 98.9% of the total variance. The inks were not well discriminated against one another. However, for the LDA model, these 3 clusters were statistically recorded at 94.37% of correct data classification, which fell within a reasonable acceptance rate. The analysis was furthered by incorporating the origin and altered ink into the PCA model. The scatter plot shows 2 clusters with 73.1% of the total variance. Each cluster did not seem to have distinguishable ink, which is then the LDA was performed to discriminate the inks. The LDA scatter plot shows that only 3 inks were successfully distinguished with a reported cross-validation of 91.37%. In conclusion, VAC analysis reported successful detection of origin and alter ink for sample check B, C, D, and E. For ATR-FTIR analysis, it revealed similar chemical composition for all 5 black ballpoint pen ink, which proceeded to chemometrics to observe the underlying pattern of the spectral data. PCA models also reported to be not exceeded for 90%, while ADA cross-validation values fell within the acceptable range of 90% to 99% of classification. Hence, PCA and LDA results can be used to support the ATR-FTIR analysis. Due to the smaller written ink on the question documents, this study has certain limitation when the bands coming from the ink and paper overlap. Therefore, I would recommend using micro ATR-FTIR to complete the analysis in order to determine the ink spectrum. Next, a pen's formulation may be the same or vary depending on the brand. Consequently, by compiling a complete database on ink formulation that include details on brands, formulation and manufacturing process, this will make it easier to compare and recognize unknown inks. These are some references that I have used. That's all from me for this FYP presentation. Thank you.